Matthews again. He is a climate scientist and senior lecturer at the Environmental Geography at King's College London. And he is very much interested in societal impacts of climate change and is currently leading a multi-year project studying the threats from the planet's most extreme weather. So just wanted to say for Project WERA, HydroMet actually donated the Kippenzonen CNR4 net radiometer, the Luft SHM31 snow depth sensors, Ott Parseval present weather sensors, and also Ott Pluvio weighing rain gauges. And we are also committed to supporting in reviewing the data to see what that looks like and, you know, eventually be improving, hopefully, our sensors, not by that much. Okay, I hand it over to Dr. Tom. Thank you.
Thank you. The slides, we have the slides.
Oh, yes.
Check.
So sorry.
So thank you everyone for joining. Here we go. So I'll begin by just, for those of you that were at the main talk, I'll begin by refreshing your memory of what Project WERA was. For those that weren't, I'll bring you up to speed with the project. So WERA, now I asked this question over there, and no one knew the answer, but now I can test you. What does WERA mean? Wind, exactly. It's a Quechuan word for wind. And we thought it was very appropriate. We suspected that Aconcagua, highest mountain in the western and southern hemispheres, highest mountain outside of Asia, might have the fastest winds in the world on the summit. We suspected they might. They probably don't, is a spoiler. We've seen enough data, they probably don't. But anyway, it's very prominent mountains, it's very proud of the surrounding terrain. This is the southern face, 3,000 odd meters. This is a view from somewhere called Plaza Francia. We actually climb the other way. We climb on the northern side of the mountain. It's a much more gentle ascent. Believe it or not, this has been climbed, this southern face. If you stand here for any length of time, you will see avalanches coming down this face, rock falls coming down. So rather them than me, I was very glad to be going the other way. So to recap, and I think I said this over there, but maybe didn't give much detail. We wanted to install a network of stations on Aconcagua, one at the summit, and you'll see pictures later from the summit, but also two lower down. One at Nido de Condors, so that's the second camp on the way up, about 5,400 meters, and one at the main base camp on the northern side, 4,700 meters. And there was already a station there that had been running for some years, but we wanted to upgrade it. And that station was run by IANIGLIA, the Argentinian Research Center. And a reminder of why we're doing this. Right, so I will talk about the climate safety bit later, because I didn't really talk about it much on the main stage, but it is really important. The main reason that we're interested in scaling this up to, why Project WERA that I'm talking about now, why we hope it's just, if you like, one of many yet to come, is because of the tremendous change that's going on with the water cycle at high altitude. So worldwide, popular statistic, very important statistic, about 2 billion people live downstream of glaciers. And glaciers are natural reservoirs, so they provide water in otherwise hot and dry periods. On Aconcagua, snow cover is less extensive than it used to be. The glaciers are retreating, and the Mendoza River that Aconcagua feeds is mostly snow and ice melt fed. So the changes that we're seeing are really, really concerning. And I think I showed you this on the main stage. For those that weren't there, I just want to point out this is part of a very profound change that's underway. In the southern Andes, we've seen 600 gigatons of ice lost in the last 20 odd years. And a gigaton is a cubic kilometre of water. So just try and imagine that, 1,000 metres high, and picture, maybe go to the banks of the Danube, look a kilometre up or downstream and imagine this block of water a kilometre high. 600 gigatons lost in the last 20 odd years. Worldwide, so that's in the southern Andes, worldwide that figure's close to 7,000 gigatons. So you can just imagine them all sailing out to sea as this mass is being lost or transferred. And what does that really mean? It means that this these reservoirs are being depleted. Doesn't mean there's less water necessarily flowing through these catchments, but the reservoirs are being depleted. The supply of water to these downstream communities is likely to be less reliable going forward. And very briefly, the challenge when we try to project what could happen next, so given certain scenarios of global warming, 2, 3, 4 degrees of global warming, the question we have, given that context, is okay, what does it mean for water resources downstream of glaciarized catchments, or catchments that get a lot of water from snowmelt? The example I like to use, and to illustrate how complex that is if we try to imagine the impact of, or think through what the impact of warming air temperatures could be on snowfall. Now, as the atmosphere warms, probably all are familiar with the idea that it holds more moisture. About 2% is the change in total precipitation we expect per degree of warming. So if all of our snow is occurring at temperatures well below zero, a warming atmosphere might just mean more snow. But if that precipitation is occurring just around 0 degrees Celsius, that warming might mean more precipitation, but it's all falling as rain now instead. So there's no mass input to the glaciers, no snow input to this system. It's rain instead. It runs off immediately. So we don't have this, it doesn't play this buffering role. In order to understand what the impact of warming could be, the point is we need to know what the current weather is, or the current climate is. We only understand the impact of climate change if we know the baseline upon which that change operates. And the context for Project WERA and the other efforts that we've been involved in sort of very high altitude stations is there are almost no observations when we get to the high mountains. And you see that depicted in this schematic from my colleague Baker Perry here. And this is a Bolivian catchment. And just for your reference, Aconcagua was almost 7,000 meters high. So there was, as of 2019, there was nothing anywhere near that elevation installed. Back to Project WERA now, so you've had some context. This is the base camp. And our first station, does this point to, it does work, you can't see on the screen. Second biggest base camp in the world after Mount Everest. We used to be able to stay in a very nice hotel here that is now a wreck. Apparently, when they left the hotel, it didn't take long for the basement to fill with ice. So there was water creeping in through the walls in the summer, and then in the winter it froze. The basement turned into a giant block of ice. You obviously can't stay there now. Our weather station, base camp, is going to be just over here. I'll show you in the next slide. Here it is. We're very pleased with this station. It's got the op pluvio that Jay mentioned at the beginning here, surrounded by a double auto shield, so it's minimising that undercatch. And we've also got Parsable here, so giving us the present weather, a camera looking up at Aconcagua, and then we've got temperature, relative humidity, radiation. The CNR4 is measuring that. We've got the RM Young Alpine sensors as a modified one with a smaller diameter propeller, polycarbonate propeller, and we're transmitting via GOES. I'm also measuring the soil temperature here as well. And inside we're running a Campbell Scientific data logger. Now, the climb from base camp follows this red path that you see marked here. There is another camp here called Camp Canada. One night here to help acclimatise on the way up, and then Nido de Condors, nest of the condors, is just here. This is 5,400 metres. That's about 100 metres higher than Everest Base Camp. From there, this is the approximate route to the summit. This is our station at Nido de Condors. So we're installing here at an altitude that's sort of in the upper accumulation areas of the glaciers. You don't have a glacier here, it's a very windswept face, but you can see the glaciers just over the way there. We do have an op pluvio Parsable sitting just here. So we're also measuring precipitation at this altitude. And I think that'll make it one of the highest precipitation sensors in the world. We don't have anything as high in our Everest network. The highest station on Everest is measuring precipitation is 5,300 meters. So going higher then on Aconcagua, and I'll come back to some of the motivations for having a network of stations when I show you the data. But for now, recognise I'm taking a journey of installing the station. So we've been at base camp, we've just been at Nido de Condors, where we've had a night, and then we're climbing higher towards the summit here, and you see this beautiful shadow of Aconcagua when you're on the way up to the top. Oops. So now I take you to the summit station, and another view of that southern face of Aconcagua that you saw at the beginning of the presentation. You were looking at this face just here, and now we're on top. We've actually had to walk over the top of the mountain, which is up here, and down the other side. The top was full of tourists. Can you believe it? Or climbers, we'll call it. It was actually a wonderful day weather-wise. It was only -10, but felt even much warmer in the sun. You could, if you wanted to, strip off to a base layer and sit there and take your time working. But he points out that one of the team here is on oxygen and had to be evacuated. We're right at the threshold of, even if you're acclimatised, where you can climb to without bottled oxygen. And that's relevant in a few slides' time. So remember that, the importance of bottled oxygen and this kind of being at the physiological limit of altitude. And here you go, here she is, the beautiful summit station, which you may recognise over here during testing. So we've got the picture of the station down there at base camp that we were testing. We were writing different programs, checking the transmission and so on at base camp. And then here she is now deployed at the summit. So this differs from the lower installations. We don't have the Pluvio, the Parsable. There's no way we could, well, you might be able to secure the sensors, but there's no way we could carry the auto-shields up there and gather meaningful data at this altitude. It's just under 7,000 meters. It's a custom tripod. This is the Campbell Scientific tripod that was honed in deployments on Mount Everest. It's the same design that is at the summit of Mount Everest. It's extremely light and extremely strong. So we work with the engineers there to help ensure that it should be able to withstand winds of well over 100 meters per second. It's bolted into bedrock. Here we have these Pelican cases carrying these lithium batteries and the data logger, and they too are bolted to the bedrock because we're guarding against extremely strong winds. We have solar panels, 3 solar panels, different orientations, different heights to try and guard against snow accumulation and ice accumulation. The strongest winds should be coming from this direction, which you can guess if you know what this is. So who remembers what this is from the main talk? Anyone on the call? It's a pitot tube. It's the same technology that's used on planes to measure the wind speed. It works the principle of it's measuring dynamic pressure. No moving parts. One of the biggest challenges in terms of a variable to measure is wind at these altitudes. It's extremely strong. Will rip the propellers off, particularly if they're covered in ice. So we have this pitot tube developed with in collaboration with the Mount Washington Observatory. It has no moving parts to measure, hopefully, the strongest winds. It can't rotate, so we just have to point it in the direction that we think they're coming from. So we point it into the west and hope that we can capture the winds. It has, I think, a 90-degree angle of attack that it can capture. We have the CNR4 contributed by Ott. You can't see on here at the moment, but it was installed on one of the cross arms. And to detect snow accumulation, we have the acoustic sounder there. That's me installing there. Any questions about this array? I know that everyone's excited by the sensors. I'm usually so. I normally give talks that are interested in the data or the experience, but here everyone's probably interested in the sensors. So yeah, please go ahead.
Yeah, thanks, Tom. I was just curious, you were saying this is like a custom-built tripod. Actually, what's the material and actually
it's
what was the whole process?
It's aluminium.
Okay.
Yeah, but it's, I think, a special type of aluminium. It's very light and very, very strong.
Okay. And what was the whole process of coordinating with Campbell to get this?
So this dates back to 2018, 2019. We worked with their engineers for many months, giving them estimates of what the summit weather on Mount Everest would be like in terms of the winds that we estimated from the analysis data and the temperatures that we expected the station to endure. And then the engineers did some finite element modelling to work out the forces that the station would likely be exposed to. So we'd give them scenarios and say we want to put these sensors at this height, which will have this surface area. Can you work with that to give us an estimate of of what it would take to withstand that. What do the feet look like? So where are we gonna? What's the best way to secure them to the rock? So we'd have this iterative exchange with them, where essentially our constraints would be: we want to measure this. The sensors are going to have to be about this high, and they would tell us what we had to work with in terms of the sort of the space to put bolts in and so on. And they came up with this design. The tripod has worked very well on Mount Everest. It's withstood winds that we've measured at over 60, probably closer to 70 meters per second, and probably much, much stronger. The tripods have remained standing when, in some cases, everything else is gone. So the tripod's good. Sometimes, in one case, the rock was less good than the tripod. The foot was ripped out of the rock. The rock had broken, but the tripod was still intact. So now I can go on to what happens to the data. So we're using the GOES telemetry system to feed data to the NOAA DCS, and we have our own computer codes to scrape that server to get data from the Aconcagua network. And then INEGLIA, the Argentinian research group, they have their online portal where you can view the data. And then we also, and we're talking about some of the main stage, if you like, the ad hoc nature of the way some of the data are let's say, organised and used after they're transmitted. And I tell you, the way I access these data is via a Google Drive. So I have my own code to take these data and then put them into Google Drive, and my collaborators share that way. It's extremely ad hoc and not at all scalable. I think I'll show you some data on the next page. Yeah, so this is a plot produced by all my collaborators at INEGLIA, Maxi Viali there, and you're looking at data from the Mulas station. So this is the base camp station, 4,700 meters. It's come in via the GOES telemetry system. This is our hourly data. So we have lots of tables on the logger. It's a Campbell Scientific logger. And we have a number of tables. The GOES table is just transmitting hourly samples or hourly totals in the case of precipitation. There's a few interesting things in these plots. So the next one is possibly more interesting than this. Well, no, just one thing to point out very quickly is how useful these very simple numbers are. Total precipitation, right? Something that we did not have any idea of before we went there. Reanalyses data, satellite products, they're just no good in such an environment. So you have to go there, install sensors, in this case it's the Opluvios, to get an idea of just that very, very basic descriptor of the climate. How much precipitation, how much water is falling to the air. So what we found on Everest, just to highlight an interesting finding where we've got a longer record, is how much more snow, how much more precipitation there was at high altitude than we thought beforehand. The whole hydrological cycle, much, much more intense. And I suspect we're going to find the same on Aconcagua. Aconcagua, an environment where we have lots of convective precipitation during the summer, and then we have these frontal depressions, we have atmospheric rivers during the winter. So we're very much looking forward to seeing how much precipitation we get during these extreme events in the winter. So you've got temperature and pressure on the top plot there. You'll see this more clearly at higher altitude, but they co-vary very, very strongly at high altitude, which is very different from what you see in the valley bottoms. And we've got this is distance to the surface. This is coming from the acoustic sounder in the second plot. It's been corrected. So this is, you see here is a snow pack where that's deviating from zero, and then you have the present weather codes and the total precipitation in the middle plot, and then we have wind speed and wind direction in the bottom plot. So we're going up a little higher here. This is the NIDO record. You see this correlation between temperature and pressure coming out more clearly at this higher site. So remember, this is 5,400 meters. You've got, what's that, about 50% of the atmospheric pressure, the sea level pressure there at this altitude, so 50% of the available oxygen. And then total precipitation, we've climbed only less than 1,000 meters, and we've cut the total precipitation in half, climbing that much. But a huge caveat: the auto shields didn't get installed at NIDO yet. We're going to install them probably this February. So that means there's a lot of undercatch error at the moment on these for these data. We also have the Luft laser sensor, also contributed by OT, that's operating here. We wanted to put it here because it's a windier site, and we know these windy sites really cause problems for the acoustic sounders. So we'll be looking, once we have a longer record, we've got a whole winter's record, we'll be comparing the laser and acoustic sounder in more detail. The summit data I haven't shown you on here. It stopped on the 8th of June, so it's a much shorter record. But we did learn some very interesting things, some very, very strong winds. So we regularly had winds over 30 metres per second, touching 40, 50 metres per second for individual gusts. We lost transmission probably because of a lack of power. And there will be an expedition going in February to try and bring that station back to life. It's probably been logging for much longer than it was transmitting, so we're looking forward to seeing what's on the logger. Now, the benefit of having a network, one of the reasons we want to have a network is that we can try and estimate how these critical meteorological variables vary through space, right? So what can we learn about from these point measurements that are useful for understanding, for example, snow accumulation, ablation over catchment scales. And once we've got a network of stations at different heights, we wanted to span a large elevational gradient. We can then deduce things like the lapse rate, so how the temperature changes with altitude. And you see it's really, really variable through time. So we've got sort of very, very close to dry adiabatic lapse rate, lowest value on the y-axis there, about minus 10 degrees per kilometre. We're going up to, consider this is, you've seen pictures back on Cadwin, exceptionally dry environment. We have lapse rates as shallow as, well, minus 5.5, something like that, degrees Celsius per kilometre. And that's probably coinciding with the passage, this is during the winter, the Southern Hemisphere winter, it's probably coinciding with the passage of an atmospheric river, or at least a frontal depression. Now, I just want to show you a few really interesting things the network is starting to show. Bear in mind, we've only got a little bit of data here, and what I've been showing you so far are data transmitted. Right, so we have the so-called GOES table on the Campbell logger that is mostly hourly samples for most parameters, but hourly totals for the odd pluvio and the sample synoptic code on top of the hour. But on the logger, we're also storing minute data. We learned a lesson with the Everest deployments that if you can store data at much higher frequency on memory cards, then you absolutely should. The challenge is trying to get these stations to run for a long period of time, and we're really challenged in doing that at high altitudes. They're not going to last very long, the stations, before they require maintenance. And it's so difficult to get to these sites. You want to record everything you can when you're there. What we also learned from Everest and other deployments in the Andes at high altitude is it can be exceptionally sunny. And I know that sounds like I'm stating the obvious, but it's the degree of exceptionality that makes it interesting. We see more radiation recorded by these sensors than you get impinging on the top of the Earth's atmosphere. So we see values much higher than the 1,367 watts per meter squared we see at the top of the Earth's atmosphere. And this is a day where we saw repeated excursions above that top of atmosphere value. It's relatively sunny, but we've got this broken cloud deck. What we're likely seeing is forward scattering on the edges of the clouds. It's been documented elsewhere. And when we look at the minute data from when we were there, we can now see this in much greater detail. We'd seen it in the Everest data when we were just logging the hourly maxima. We'd seen it going above the top of atmosphere value. I had no idea whether that was once or whether it was several hundred times during the hour. Just logging the hourly samples, you can't even see it. It's not the best plot, I apologise for that, but this yellow line is frequently going up above the red line, which is the top of atmosphere value. At a time when the thermal emissivity, the proxy for cloud cover, is also much higher than normal. So what we're seeing is as that broken cloud is moving through, we're regularly having solar radiation well above the top of atmosphere value. Why does that matter? Because it's the total energy that's impinging on a snow or ice surface that determines whether it goes above the melting point. So if we use the average flux over an hour, that might not be enough to drive it over the melting point, but if we look at higher resolution, we might frequently have crossed it for very short periods of time and had some melting. So the value, there is tremendous value in one, having these high quality sensors that we can trust to monitor solar radiation in this environment, and two, having, to our conversation earlier, having multiple data tables. So we've got something we're transmitting, it's lightweight, through GOES, and then we've also got, because we can store this data on these high volume memory cards, we've got data at much, much higher resolutions, giving us a much richer picture of what's going on. We also saw, I don't have it in the slides, but we saw a rain event at base camp when we were there, exceptionally rare. None of the guides climbing, some of them for 30 years had seen rain in the summer, but we recorded it with in high frequency with the in some of the tables on the logger. Now, one of the last things I'll give you is one of very busy slides. We focus on the story, and then I'll point to the relevant parts of the slide here. I said that one of our team had to use bottled oxygen on the summit of Aconcagua, and I've alluded to a few times now the other reason for putting weather stations on the tops of some of these mountains is because lots of people are risking their lives to climb these mountains each year, and a good weather forecast can potentially save lots of lives. Now, Aconcagua, it turns out, is one of the deadliest mountains in the world. You would not expect it because it's pretty easy. It's a walk. It's not very technical. Forget that southern face. A few people climb that. Most people walk around the back. But it's deadly because lots of people do it. It's very accessible. And it averages something like 3 deaths a year. And most of those deaths are from pulmonary edema. And it's essentially the lack of oxygen that's killing people. They're getting very, very ill. So if you could forecast, well, let me step back for a second. I tell you the amount of oxygen on the summits of these very high mountains changes a lot from day to day. More in the winter, when the synoptic variability is higher, but it changes from day to day. And to give you an idea, I won't go into detail how you do this, but the physiological height of Aconcagua, how high it feels, varies by something like 800 meters, depending on what day you climb. It goes from about, not much actually below the average height of 6,900 meters up to well over 7,700, something like that. It really matters which day you go. It's the same we've seen on Everest. It's about 800 meters the difference there between the best day and the worst day. And just with this very short record we have from the summit, we can immediately correct things like reanalysis data to the observed air pressure. And just to say, the oxygen, because of well-mixed gas, the availability of oxygen is proportional to the barometric pressure. So we can very easily work out the variations in barometric pressure, and elsewhere work has been done to see how that translates to how difficult it feels for climbers, the physiological effect. So for this very short record of the weather station and summit, we can quickly correct and get long-term statistics of how much the physiological height changes on Aconcagua. Nothing particularly exciting for saving people's lives there, but a much bigger opportunity that we're looking at across this sector that was alluded to briefly in the panel is you can have very lightweight AI systems that are correcting to observations. So model output statistics are like, it breathes new life into it in scaling and making more sophisticated the algorithms that are available. So what I'm showing you here are some of the results of applying a simple machine learning algorithm to the GFS forecast, and you're looking at skills and predicting the physiological height of Aconcagua at different lead times. This is a 96-hour lead time, and you see it's incredibly skillful. It's very, very easy to do. That's all out of sample predictions. It's very, very easy parameter to predict because it's essentially temperature in the free atmosphere. I showed you how well temperature and pressure were correlated earlier. So essentially, we have a new forecasting product here for the high mountains, which is the amount of oxygen that's on the summit on any particular day. It could save lives in Aconcagua, almost certainly on Everest and the other high peaks. Only possible because we've got the station sitting on the summit. Everything else is off the shelf. It's relatively straightforward to do. So I think, obviously, we've got time for questions on any element of the data. The more serious, I'd say the bigger scale sort of impact on water resources, glacier modelling and so on, that will follow when we get more data. I've given you a taste, I hope, of the type of data and the type of challenges that are involved in a project like this. But this, right at the beginning, I suppose I could have highlighted this more, but I've got the opportunity now. It's only possible because of this collaboration between research partners and corporate sponsors. It takes many hands to do work like this. So yeah, thank you very much, and I'll now stop for questions.
Hey, thank you very much, Tom. That was really super interesting. I've not had much to do with this particular project. I work for Campbell, so one of the other folks involved, and thanks again to Watt for letting us come and listen. I started my career with the UK Met Office as an observer. So that was my first job back in 1978, so it shows you I'm old. I was using equipment analog as we were switching to digital. I guess one of the things I kind of got interested in as well is not just synoptic observing, was road weather. And when we first started putting equipment onto the roads, we didn't have a clue really where to place them. And we were finding some real anomalies. Some of it was obvious, things such as we go and put them prior to a set of traffic lights, and then suddenly we find that cars would park over them at rush hour, and you're getting some pretty odd, readings. And I guess my question is really for you is, do you think you've got the ideal location? I mean, I know most of the time it's restricted because of access, and where would you like to put them? And do we think that we could probably see some even more weird extremes if you put it on a different part of the summit?
Yeah, so a very, very good question. We are, firstly, thanks again for the support from Campbell to these different projects over the years. So we are extremely restricted in where we can put them. There's a story here from Everest that points to the problem sometimes with where you end up being funneled towards. So in 2019, the highest we got was a place called the Balcony. It's this place midway between the highest camp on the Nepal side and the summit. We intended to go to the summit that year, but it was crowded and everyone was moving slowly, so we chose that site for the highest station. We hadn't ever thought about it prior to that night. It worked in that we put the station in, but eventually this is the one that got pulled out of the ground, where the rock failed. And we think also what was happening was that site is typically sheltered from the prevailing wind, slightly sheltered. And occasionally what happens, you get these eddies that break off the summit, and you get these incredible gusts. And we think that's probably what took it away. And there's some anecdotal evidence to support that, and also to highlight what sort of environment we're talking about up here and why forecasting the weather is so critical. In the same spot, a mountain guide passed on to my collaborator Baker. One year, because we were talking about these, we called them road gusts at the balcony. He said one year he was climbing, it was a relatively calm day, at least it had been from the South Col, which is where this highest camp is, up to the balcony. And he was clipped to the rope, as you normally are, and he got to the balcony, and the next thing he knew, he said he was like a flag. He was flailing, his feet were off the ground, and he was just held to the mountain by his rope. So it's the same spot. No surprise when you look at the numbers, but I mean, does anyone have a sense of what that would feel like, other than being absolutely terrifying? No. So we are hugely constrained. What you see in the sites that we choose now, it's foot traffic that we're trying to avoid, because the Everest Summit Station, it's getting hugely constrained. It is right, you might have seen pictures, I don't know if you have, but it's right on the main climbing route. The rope, it's about where you are, Jay, from where the main climbing route is. So if there's a bit of leeway in the rope and someone's tired, they might go and lean on. So human interference is one of our biggest problems up here. On Aconcagua, the reason why we went up and then down again side of the summit was precisely because of this reason. The footfall, and also in some of these sites, people are not happy with weather stations being on top of these really enigmatic, pristine mountains. So we have to move off a little bit. There's another challenge in that because the flows are so complex in mountain environments. What are we really measuring? Are we measuring winds that are representative of anything other than the ridge or peak that we're on? We think so, the likes of Everest and Aconcagua, because they're such prominent mountains. I mean, you're above the surrounding terrain. But certainly some of the lower stations, the winds you have to take with a pinch of salt. Yeah, good practical question.
Sorry, me again. So before you were showing the two of the stations, the Mulas and the Midang, like you both have the particle installed, so you're really looking also at like the phase of the precipitation, right?
Yeah.
So I was just understanding now about the particle, talking to Martin and Elton, and actually then this is quite a strong power draw as well, right? Do you actually have power-related issues then at some of those stations, or is really the incoming radiation or like the power that powers in there?
No, good question. We do. Power is always the well, I'd say the primary constraint. Once we've forgetting placement for a second, the power is the problem. So the Parseval, we're running it more frequently here than we did on Everest. I think we're running it 4 times an hour. I'm not sure, but we're not running it as frequently as we'd like to. So we just have code in the program that turns it on at different times. So we take a short sample. It used to be just top of the hour. I think we're doing it 4 times an hour. Even with this incredible solar radiation, the power draw, you have to be prepared for the winter. So it's not what you can get during the summer when it's at its best. It's what you can get during the winter when there's not much radiation at all. Okay, and so if there are no other questions, thank you very much for coming to listen. Thank you.